Hey everybody, and welcome back to Algebra 2 online. So the plan for today is to just talk about some harder problems related to graphing logs and exponentials. There's some function transformations with them that can definitely be a little bit confusing, and I just kind of want to deal with those for a whole day solely. So to start off though, just kind of unrelated to that, I have here the three kinds of functions that cause domain issues. Really three classes of functions, because you can have infinite amount of logs that have a domain issue, an infinite amount of rational functions, and even root functions. So over here are the three pictures that kind of go with these three. And all of these, right, when you look at these pictures, you can see there are cutoffs in the x. Here it's just a point. Here and here it's a whole bunch of stuff. But these graphs are the three graphs that you'll see this year that have some weird domain issues. And anytime you run into domain issues, you run into some tricky stuff when it comes to solving them, because you can solve things out and it looks like certain numbers should be answers to problems, but those numbers may not be in the domain, and so you have to throw them out, that kind of thing. So I just wanted to go through and basically compute the domain for these three, just to kind of sum up the three big issues. So maybe we'll start at the bottom and kind of work our way up. So, we did these very recently. We know that for those ones, we just take whatever is inside, right? And we just set greater than or equal to 0. So here, x would just be bigger than or equal to, nope, not 2/3. Be bigger than or equal to 3/2. And so it's hard to see, but that's x equals 3/2, that vertical line. And that root function is defined just bigger than or equal to 3/2. This one right here is just a rational function, and we know for these ones we just have to be worried about the dividing by 0 issue, right? That is something we don't want to happen. It's a bad thing, right? So we just want x plus 1 to not be 0. X just can't be -1. And that is what we have right there, right? The vertical asymptote at -1. And then logs we just saw recently, just last class. But for these ones, it's so close to even roots, except we know that, the basic log can't touch the y-axis. And that means that the way to find the domain is to just take the inside and just set it specifically greater than 0. So as down here, we can definitely take the fourth root of 0 and get 0. We can't do log base 3 of 0. That does not make sense. But as long as this inside is greater than 0, it'll be defined. So here, if you solve that out, you get x is bigger than 11. And that is what is right there. So, basically the way I look at this log is you got log base 3, and if you take a 3 out, you have x minus 11, right? And we know that function transformation-wise, this shifts the graph 11 units to the right. So that is algebraically how you find the domain for all these different log functions here, or these different functions. And these three are the three kind of annoying, messy ones that we'll have to deal with this year. Really, besides this, everything else will be pretty nice. All right, so this is a very important and very subtle little question that we didn't actually have this pop up in the homework, and I did that on purpose because I didn't want to overcomplicate the first day with these things. But if you have, so this function g and f, and if you were asked to graph these, the way I want you to do it is just to plot one point, okay? And we know that normally, right, a log function goes through this point 1, 0, and just kind of that's what log growth looks like. That could be like log base 2 of x or something. And then if you had log decay, maybe this could be log base, 1/2 of x. Both of them would be asymptotic with that, right? Y-axis, that's kind of like your normal one, okay? Now here, there's two function transformations going on. Here, there's only one, all right? And if we just go through the function transformations, here this 2, what it does, right, is you would think it's horizontal stretch, but it's actually the weird backwards thing inside, so it's horizontal compression. So for this one, we normally would be at 1, right? And then the 2 inside here happens, and we go to 1/2, right? And then this 2 in front acts as vertical stretch, but we are currently right there, and all it does is it's going to multiply the output by 2, but the output is 0, right? So we're just going to do 2 times 0 right there, and so it'll just literally stay right there. So that graph would literally look something like that one. This one, though, you don't have really an effect on the nice point at all. Like there is no, it's just 1 in here, and there's nothing horizontally changing this point. So you literally just stay there at 1, and the 2, really just does, like, it changes the steepness, but we don't really see that, and there are asymptotes here. And that would be kind of it. So this one, the nice point you would plot is the normal old 1, 0, and this one it would be 1/2, 0. This kind of stuff is true too for exponentials. It can kind of be weird like that. If if you have like 1/2 times 2 to the x or something like that. Now, like, the way you would plot this kind of graph really quick would be, normally it'd be going through 1 or 0, 1, right? But then I need more room. Normally it'd be going through 0, 1, but this 1/2 acts as a vertical compression, so it actually would be here at 1/2. And so it's a growth 1, so it's going to kind of just do that. And I missed the point. But those kind of scaling, whether they're outside or inside, those kind of things can definitely be pretty tricky. So I wanted to specifically talk about it for this simple graph and this simple graph, because I want to do harder ones now. So right here, I just want to do some just kind of sketching, but these are definitely harder than the ones you had to do in the homework for last class. So let's do this one in blue, let's say. The first thing to kind of think about is just that nice point for exponentials. So normally we'd be right there at 0, 1, right? But the first transformation is a horizontal compression by 2. And so, there's no way to squish this in anymore. So that 2 does nothing, right? Then we have a 2 in front, which is going to do something. It's going to move that point from here up. It's going to double it and be up here at 2. Then there's a negative happening, right? So we know that's a vertical flip. So now we're down here at -2. And then there's lastly a +4. And so then we just move that point up 4. So we're at -2. That's moving up 2, and then that would be moving up 4. So that is actually where my point ends up. So let me just go through that again. So we started at 0, 1. This 2 inside does nothing. This 2 on the outside does something, moves it up here, scales it by 2. Negative happens, flip, right? 4, shift up 1, 2, 3, 4. That's where we're at. And in terms of if we're doing the shift part here, we knew that the asymptote was here before, but that asymptote will move up 4 because of the plus 4. So we do have a horizontal asymptote up there. And in terms of the shape, right, we had a base 2 exponential, so it was growth, but we had this flip happen. So this thing gets flipped down, and then it was like shoved up, right? So it was kind of like, looked like that, then it got flipped, and then it all got pushed up, right? So what you get is basically that kind of shape, right? Because it was just flipped. It was normal, base 2 growth exponential. Then it got flipped, so now it kind of looked like this. And then at the end, we just shoved everything up 4, right? So we're up there. So that's the first one. Let's do the next one in red or something. So for this one, I would start at 1, 0, right? All logs go through 1, 0 because all exponentials go through 0, 1. And then this 3 acts as horizontal compression, right? So it basically should take it to 1/3 instead of 1. So this is 1, those are thirds basically. So now we're at this tick mark right here. And then there's a 1/6 vertical stretch, right? But that 1/6 really won't do anything because, it will, but we can't really graph that. And I don't expect you to graph that. So that 1/6 will just basically vertically squish it. So, if my log kind of looks like that normally, maybe the 1/6 one is going to be a little more squished, kind of like that. But those things are harder to show. So I don't need you to really worry about what the 1/6 does for this one. Then the last thing is the plus 2, right? So we're going to take this point and we're going to go up 2, which is right here. So the nice point on this one is 1/3, 2. The nice point here on this one was 0, 2. And then in terms of shape for the log, right, it was base 2. So it was a growth log. And we never did a shift left or right. So it still has an asymptote right there at on the y-axis. And then we just kind of draw in something like that. And that's it. And that's basically as hard as graphing logs or exponentials can get. There's not too much more to say with it, just take some practice. A lot of just like function transformations, and all I'm looking for is 1 point, a dotted line, and general shape. That's all I basically will be looking for. All right, so I'm going to kind of switch gears here and talk about a very, very, very famous exponential function. It is literally so famous that they call it E because it's short for exponential. It's kind of the exponential function. E to the x, this is actually like a number, E. It is 2.71828182884. It does have a weird pattern. It doesn't just go 1828 forever. It does change, which is why I went to 4. But it is like pi. It's one of those numbers that is irrational, and you can't write it as a fraction. And it actually is very useful in a ton of applications in the world. It shows up in calculus all the time. You might notice my board has E's written all over it at different times. And it's a button on your calculator, just like pi is a button on your calculator. Super famous. It's just a number. At this point, you've already heard about I this year. You know about pi, E. There's this symbol is something called phi. That's a famous one. There's something called tau, which is another letter that's a number. There's so many other ones. So really, honestly, too many to list off right there. But I want to kind of go through how you get this number. So this famous 2.718 thing. So it was discovered back in the 1600s by this guy. This is a guy named Bernoulli. And basically, back then, math was all centered around finance, a lot of it at least. And he kept noticing this number basically popping up, and it became like so important through his research that he was like, well, I might as well, instead of basically writing this whole thing down, I'm just going to call that thing E. And I notice it just shows up here and over and over and over again. So this is kind of the easiest way to just explain it. So if you have an account that starts with $1 and pays 100% interest, which is absolutely crazy. In the real world, interest might be more like a fractional percent or something like that. But that is like the theoretical startup point, okay? So the interest, we'll just say, is credited once at the end of the year. So it's just applied, the year goes by, and then you just apply it. So the value of the account will be $2, right? The dollar you started with plus the $1 you get from interest, because you get 100% of your dollar at the end of the year. So assume you don't touch any of the money and stuff, right? You just let that 100 sit there. You would have $2 at the end of 1 year, right? So I'm going to let n basically be like representing the years. So that would be like n equals 1, all right? And that, oh wait, I'm sorry. The n is the number of times that you apply the interest in a year. So, so instead of n equals 1 times per year, we could do n equals 2, which means that we apply still the 100% interest in the year, but 50% each time. So maybe in June, halfway through the year, you apply 50%, and then in December, you apply the other 50%. N equals 4 would mean that you're applying the 100% spread out over 4 chunks, so like quarterly, right? So, every 3 months, right? You apply 25% of the interest, basically. So what I want to calculate is the amount of money in the account as you increase the interest, application times throughout the year. You don't increase the total amount of the interest. You still have, like, for 2, 50% each time. For 4, 25% each time. So it always has to add up to 100%, but you're doing it more often throughout the year. Okay? So for n equals 2, right, it would look like this. It would just be $1, right, times 1.5, because you want to keep your dollar, which is multiplied by 1, and then you get 50 cents, you get 50% more, right? So you multiply by 1.5 to get 50% more. And then that's just one time, but we need to do it twice in the year. And if you multiply those out, you get 2.25. Okay? Another way to have just written this, right, is to not do it like that, but you could have just done 1.5 squared, right? If you want to do n equals 4, you would do $1 to start off with times 1.25, right? And you would do that just 4 times in the year, right? Otherwise known as 1 times 1.25 to the 4th, right? And that is 2.44, okay? And then if I do it 10 times in a year, it would just be $1 times 1.1, right? To the 10th, which is 2.59. If I want to do it 25 times, okay? So there are, basically here it's just like 25 times something, right, is 100, right? And we know that's 4, right? So that means the decimal should be basically written as 1 times 1.04, right? This is like a decimal of 0.10 because there's 10 tens in 100, 0.5 because there's 2 50s in 100 and so on. So so if I do that 25 times, okay, throughout the year, I get 2.6658, right? And so what you might be noticing is these numbers are getting closer and closer and closer to this number. And that is actually true. So if you look at what we're doing here, what we basically are doing is a limit problem. And that is actually the formal definition of E that I want to write down here. So we're going to do this in white because it's so important. So basically, if you look at the progression of what's going on, it's basically like 1 plus 1 over, so 1 plus something really small. And we do that n times. And if you let that n go to infinity, all right, so you're literally doing one of these kind of like horizontal asymptote almost problems. The idea is like you take your dollar, right, and you add infinitesimally small little bits of it, right? So you can see, like, of course, 1.04 is smaller than 1.5. You're adding a super, super, super small amount. But if you add a super small amount to it, nearly infinite amount of times, right? So you let the exponents go to infinity, then this thing, if you solve this limit out, it is literally the definition of E. That is actually its formal definition. That's a super famous result in mathematics. And he figured that out somewhere in like the 1600s, I think. I think it was kind of late 1600s. But this constant, which it is just a constant, it's a number, just like pi, shows up in a bunch of applications. And so I just want to do a few examples with E, and we will use E a bunch in this course really from this point on. Just think of it as a number, because that's what it is. It's just 2.71828, this thing up here. So I'll just do this one first. So this is just a graphing kind of problem. So we can run into weird things like this. And you really just want to think of it as exponential growth, right? Because E is bigger than 1, so it is exponential growth. And so, same kind of thing as before. I'm going to kind of think about starting up here at 0, 1, and then plus pi shifts you to the left pi, right? So we'll say we kind of go about there. Then we have this negative here, which means, so we were doing growth, right, like this. But now we're going to flip it, right? And it's going to look like that, right? So after my flip, I'll be down around here, okay? And then there is a minus E. So I'm going from negative 1, I go down E, right? So it's like negative 1 minus 2.7, this weird number, 2.71828, blah, blah, blah. Which would put me, somewhere kind of down around here. So this point, we're going to say, is minus pi, comma 1, or negative 1 minus E. And I'm going to get rid of this. And then, we shifted it down E, so the horizontal asymptote is just y equals negative E. And so I feel like I didn't give myself enough room there. So we'll just say, actually, yeah, this should be more like here. Sorry, that didn't look right. And then, yeah, so now we're good. We'll just do that. So that point is negative pi, and then we're up here. We flipped to negative 1, then we went down 1 to 0.7, roughly. Definitely don't need to be exact with this kind of stuff. I just am looking for general shape again, that kind of thing. All right, so I'm just going to do one more kind of graphing question, this time with a log. I want to write down a logarithmic decay function, which has an asymptote that goes through the point 12,092, 40,398. Seems kind of weird, but actually it's pretty straightforward. So let's just say this is 12,092. And then we'll probably estimate that maybe that is 40,398. So I want my asymptote for my log to go through there. We know asymptotes for logs are vertical, right? So I don't need that point there. So I want that kind of asymptote, right? And then I want it to be logarithmic decay, right? So it needs to just kind of like drop down like that, right? Tons of things would work here, but I'm just going to do this. So I'm going to do log base some decay function like 1 over e, right? 1 over e would be decay because it's 1 over 2.718, blah, 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 which is a fraction. And then we just want to shift it to the right, 12,092. And then really that would be fine, but just for good measure and to use e, I'm going to add e, okay? So basically it's like you moved over, really, really, really close. That would be like the point here, 12,093, and then I just added plus e to it, right? And so it's like there's now a point. It's obviously the scale is like horribly off, but the point is this. I'm going to just label it. That point will be 12,093, comma e, right? Because we normally were over at 1, 0, and then we shifted, and then we move up e. And we have log decay. It just kind of looks something like that. So this one is a perfectly fine answer to this question. The important parts are that this is less than 1 to be decay, and then this is shifted over by that much.